Okay, so we will play with this. I do have my desktop set up, so in case this stops working, we'll be able to shift it. So I'm basically going through today we are going to just go through solving finite horizon Markov processes, and then hopefully, time permitting, start talking about infinite horizon Markov processes. Just to remind you what we were doing last time, basically we were talking about the policies for an MDP might either be non-stationary or stationary, right? And the non-stationary policies would be needed if you have finite horizon. Okay, so it has nothing to do with the non-stationarity of the policy, it has nothing to do with the non-stationarity of the underlying MDP. Even if the MDP is stationary, the policy has to be non-stationary for you to be able to find the optimal policy. That's the important thing. And then we talked about that, and we also, basically looked at why it does make sense to have. Okay, so we're going to go this way. It does make sense to have a non-stationary policies. And then we spent a lot of time last time talking about replanning and whether replanning would make sense. Okay, and the specific thing that I want you to remember from that discussion is if the world is ergodic, what? Yeah, so ergodic basically means that the probability that you can reach any state from any other state is non-zero. That's all it means, okay? Which by definition means there are no sync states, right? Basically, if you can reach any state, from any state you can reach any other state, and how can there be sync states, okay? So if the world is ergodic, then you can actually do replanning and live, okay? You may not be optimal. Replanning doesn't necessarily give you optimal behavior, but at least you won't die. If on the other hand, the world is not ergodic, and if you depend on replanning, then even if there was a way of actually living happily, you might actually die because you did the wrong action, got into the wrong state, and you don't have a chance of getting out of that state. Computing the policies is planning, which is before you do the action in the world, you're thinking about what actions must I do. In particular, remember that these policies essentially are telling you for every state you can potentially find yourself in. What would be the optimal action you're supposed to be doing here? Once you compute that, then you did all your thinking, and during the execution, you just start basically check which state you are in because you're fully observable. You are in a fully observable world. You can check which state you are in, and then the policy pi tells you, given the state, what is the action. Okay, and you just do that action, and then check again what state you are in, and so on. Okay. So that's basically the replanning aspect, and so you kind of want to understand that replanning is cheaper computationally. The reason many people don't do planning, I mean that's including you, is because let's just start living already. Okay, in fact, there's a famous quote by John Lennon that life is what happens when we are busy making plans. Okay. So we presumably think that if we think too much about what we're going to do, the life is moving on. Okay, and so essentially we sort of sometimes that's the right thing to do because in fact the world is moving so fast that why come up with a 5-year plan? Sometimes it's just intellectual laziness, intellectual or computational laziness. You just don't feel like finding the optimal plan or optimal policy and jump ahead and start trying to execute some actions, and obviously you would be not. Okay. However, the fact that replanning is connected to computational laziness is something that would be of use to us when after actually having figured out how to compute optimal policies, several classes from now, we'll start saying, life is too short to find an optimal policy. We know how to compute it, but it's just too long. It takes too long to compute the optimal policy. So then we will find a continuum between somebody who does optimal policy construction versus somebody who just jumps in and starts trying to swim. Okay, in between would be somebody who looks at case steps ahead and sees, given a case step look ahead, what would be the best action I should be doing in this state, for example. Okay, so those would wind up becoming approaches for solving MDPs that are more scalable computationally than the optimal approaches. So again, the thing to remember is that in CS, the difference between a computer scientist and a programmer or a hacker is you want to first ask yourself, how hard is it? What is the optimal solution? How hard is it to find it? And then throw the optimal solution out if it's too costly, and then look for the scalability. Okay. If you're a programmer, you don't ask what's the problem. You start programming. Okay. So that's the main difference here. We will actually try to understand how hard is doing the optimal policy first, and then give up and go back to replanning. Although in this slide, we are sort of making it sound as if replanning is what lazy people do. Laziness can be a virtue sometimes. Okay, if the problem is way too hard and you're spending too much time thinking about what the optimal policy is, the world is moving on. Yeah.
So what about in a world that's dynamic? Does plan even make sense then?
That's the world we are in. Of course, so the question is, so one of the big issues that MDPs don't directly deal with, that is, how do you schedule your deliberation? Okay, as you are thinking, deliberation is thinking, planning. Okay, as you are planning, the world is moving. So you can either find the optimal plan and start executing it. By that time, the world has ended, because the world is dynamic, and even when you're not doing anything, it's changed. Yeah, it's changed or it ended. In the sense, the entire problem became moved. Okay, versus you just start jumping ahead and start making some actions that would wind up basically being inoptimal, even though the world, even though you could have done more optimal behavior, you wound up showing inoptimal behavior. A classic example of dynamic worlds comes, for example, in game theory, right? In terms of adversarial games. And so that's why, for example, in chess is a deterministic game. There is an optimal policy that can be constructed. It's just, it takes forever to construct it. Okay, so what you wind up doing in chess is, in the 3-hour form of the chess, people are looking maybe 8 ply into the game tree. In the blitzkrieg form of the chess, they are just looking at the current state of the board and start making moves. Okay, so this issue of whether or not, how much planning to do and whether or not you should do planning when the world is changing, that is a central issue in intelligence agency. Right now we are acting, remember our assumption right now is the world is static. So it waits as we think about doing planning. But then when you start talking about actually applying this in any reasonable scenario, you have to consider the fact that the world doesn't stop. And so then you may wind up doing things closer to doing that. But we are jumping ahead. Let's go back and let's stop the world and then try to figure out how to compute these policies that we've been talking about. So the important thing is that you have a state S, and given a state S, you're trying to compute a policy phi, which takes state S and gives an action A that you are supposed to execute in that particular state. Okay, we are trying to compute this policy. Now, of course, as I said, there are many policies. Okay, in fact, if you are looking at if you are looking at the finite domain, the infinite domain, infinite horizon case, it is a power s number of policies. And if you are looking at the one which has a horizon t, then it is a power s times t. Those are the number of policies that are there. Okay. Now, any one of those policies would be sort of mapping a state into an action. right? So the question, of course, is how do you differentiate between a policy pi 1 and a policy pi 2? Right? That's what we are interested in doing. And to be able to talk about that, we talk about the notion of value of a policy. Okay, I sort of mentioned this in passing in the, I believe in, I don't know why I'm not getting this. Yeah, in the first 2 classes back, that the way you think about the value of a policy is when you are in a particular state, you of course get the immediate reward for being in that state. But then if you continue, doing your actions starting from that state, and you showed a behavior, k-length behavior, then the reward that you got for those k states, you can add them up, and that is the reward, that's a cumulative reward you got because you started from this state. Okay, now the actions you do in the subsequent states depend upon the policy you are using. So each policy will tell you to do a different action, potentially a different action in each of the states that you will encounter. So I'm starting from this state, I would then show k states. I'll show my k state behavior. The way I do the k state behavior is I start from the state, look at my policy to see what action I'm supposed to do, then I do it, and then I'll find which state I'm getting into, then look at my policy to see what action I'm supposed to do and do this k times, and then I'll get k states, add up the rewards, and that is one cumulative reward I got starting from the initial state, the current state. The value of this policy value of this state with respect to this policy pi is the expected value of this. So remember, that's because there is stochasticity involved. The one time you might get 0 reward, another time you might get 1500 reward, another time you might get 2500 reward, and so on. So you take the average, you take the expected value of the cumulative reward you will get from this particular state using this particular policy, and you call that the value of the state. So value of the state is sort of like the reward of the state. So we start talking about value of the state. We already knew reward R of the state. Reward is just the immediate reward of being in that state. Value, on the other hand, is a long-term property of starting your behavior from that state. It's a very interesting, if you haven't thought about it before, it's quite a subtle concept. For example, a state can have negative reward and positive value. That's what school has always been. As you're going through it, it looks like, my God, what a drag. But supposedly you are going through this because it has a positive value. It's not that you suddenly start liking school. It is that having started from the school state, you are then able to reach other states that you couldn't have reached if you didn't start from here. You see what I'm saying? That's what you do. You're doing bachelor's so that you'll get a job. You're doing master's, you get even better job. You get PhD, maybe you won't get a job. Whatever. So the point is that you're trying to improve your, the cumulative value. Okay, so it's important to understand that the reward and value don't have to be directly correlated at all. Reward is the immediate reward. A myopic person, and it's very hard to say myopic, and if you tell your friend you are so myopic, they are not going to talk to you. Right? Myopic is a bad thing. And myopic person essentially just takes the immediate reward and says, okay, this state, seems like in school I have to keep listening to somebody, whereas if I keep playing outside, that's more fun right now, or hang around in front of the TV, that's more fun right now. So reward-wise, TV is better than being in the class. And yet value-wise, to the extent you are still here, it's because you somehow believed, received wisdom that value-wise, hanging around in the school is better than hanging around in front of the TV. Okay, so that's the value part. So value is also essentially a real number. Okay, but it's the expected value of the cumulative reward that you will get starting from that state. Now this expected value depends very much on the policy you are using. Okay, so there are two things that we'll wind up understanding in the next couple of slides. One is, given a policy, can you compute the value of every state? You can, because even if you don't understand anything else, suppose I'm actually looking at a finite horizon MDP of horizon K, and I have given you pi 1, the policy, okay? So I just want you to find for every one of the states, S1 all the way to Sn, I want you to find their values. You can write a little program which basically starts from S1, does K behaviors M times. Each time computes the cumulative reward you got, averages it out. That's the value for the state 1. Start from state 2, do the same thing. Start from state 3, do the same thing. By doing this, you would have got, just as R is a reward vector over the states, you get a V which is a value vector over the states. Did you get that? Okay, so then I am basically, when I am talking about, so pi 1 essentially corresponds to, let's say, V1 value vector, and then there's pi 2 which corresponds to V2 value vector. You would say pi 1 is better than pi 2 if V1 is better than V2. Now, of course, how do you say one? I mean, if it's a real number, you can say, well, better means bigger. Okay, but it's a vector right now. V1 is a vector, V2 is a vector of size, the number of states. Okay, and so the question then is, how do you define V1 better than V2? Okay, and the thing that we will assume from now on is that basically we use max norm comparison. Okay, here's one way of thinking about it. You would say V1 is at least as good as V2 if for every state V1 of S is greater than or equal to V2 of S. Do you understand what I'm saying? So if V1 is better than V2, I mean V1 is at least as good as V2 if V1 is greater than or equal to V2 for every one of the states. And it's strictly better if there exists at least one state where V1 of S is strictly greater than V2 of S. You see what I'm saying? That's why that's how you say value functions are better. And if a policy has a value function which is better than somebody other policy's value function, then this policy is better than this policy. In computing the optimal policies, you are trying to find the policy which will correspond to a value function that is the best possible. That means there is no other policy that can have a better value function. Okay, yes?
So I'm confused for the value of the state. So you say you start from a state and do the complete behavior and come back to that state?
There is no such thing as come back to the state. Basically, so here are states. So suppose if you think in terms of your little grid example, okay, I need a value for this, value for this, value for this, etc. Okay, suppose pick some state. I suppose this state. I'm trying to figure out what is the value for this state. I have a policy pi currently. It tells me that S1 do A1, S2 do A2, etc. So I start and I'm looking for a horizon of size k. That means I live for. I know from the beginning that I'm only going to live for k time epochs. So I'm trying to figure out if I were to use this policy and I only live for k epochs, what is the cumulative expected reward I will get if I start from here? To do that, I will say, suppose this is S2, okay, I will start from RS2 because I'm already in S2. Okay, that's already one time step. Now at this point I'll go check, oh, S2 I'm supposed to do A2, so I'll do A2. A2 might some probability go here, some probability go here, some probability stay here. Now you did this A2. Now open your eyes and see what the state is. Right? And so now let's say suppose you are in S3, okay, then you will essentially add R of S3 Now you go into this place and look for S3's action and do that action. And keep doing this until you have done K actions. At this point, you have K reward numbers. You add them up. That is the cumulative reward you got on this K horizon behavior. But then notice that if you started from when you did S3, when you did A2 and S2, in your current behavior you came to S3, but the next behavior you may stay in S2 itself because that action is stochastic. You see what I'm saying? So that's why you need to take this multiple times. You need to consider the expected value. So, basically all I want to say is the expected value of this summation of these rewards. And to do that, you essentially just do it, by actually, so there's a way of doing this in this brute force way. We'll find out better ways of doing it in a minute. But yes.
Your recording may have stopped. There was a little thing that came up that said recording 20 minutes.
Oh, really? Okay, fine. No, it's still doing it. No, it's still doing it. Good. Okay, thank you. So that's basically an optimal policy is one that's no worse than any other policy at any state. Okay, and basically that's what you're trying to find. There may be more than one optimal policy because they all come up with the same value function. Yes.
Just here, you said that we are given a finite number of steps, as in our life is say something.
In this particular case, we are looking at finite horizon.
So there are 5 steps or something. So in the first step, say the optimal policy says go up, and it's not able to go up, it stays in the same state. Now it has 4 more steps of life remaining.
That's all.
So sometimes isn't it possible that the policy will change depending on?
No. All I am saying is the policy is I am pre-deciding that in this state I will do this action, in this state I will do this action. So for example, you may have decided that as I grow up, if I ever find myself in data structures course, I will work very hard and get a good grade. And if I then ever find myself in Intel, I'll probably see a lot of movies and enjoy my life. This is your policy upfront. So as and when you come to, and if you're trying to decide whether it's a good policy or not, you basically, that's what we're doing right now. Changing of a policy is figuring out what's the best policy. Before you can figure out a best policy, you need to figure out how to evaluate a given policy. That's what I'm doing right now. Yes?
So how do you exactly calculate the overall final value of the entire policy for the reward?
There is the value of a policy is the vector. It's not a single number. Value of a state is a single number. Value of a policy is a vector of size S, which is the number of states. You understand what I'm saying? So in this particular case, a 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a 9-sized vector. Okay, if I have pi 1 will correspond to V1, which is a 9-sized vector. Pi 2 will correspond to V2, which is another 9-sized vector. I would say V1 is at least as good as V2 if in every place, every state, V1 is greater than or equal to V2 for that state.
And how do you compare the V of each individual S?
That's what I was doing just now. I'm just doing empirically starting from that state, make a K-size behavior, and then find that average value. That's what we just said. Yes, there was some other question. Good. Okay, so starting from this state S2, I got a K-size behavior. I computed the sum. That is one time starting from this. That's what I got. I do it again, and I figure out. I do it again, I figure out. I do it again, I figure out. And I find the expected value. Now notice, by the way, that the way I'm evaluating the policy here, essentially I made it sound as if you need to actually do the action in the real world. Did you guys see that? Because I said, do the action A2 here and see what happens, which state you get to. That actually flies in the face of planning. Right? To figure out how good a plan is, if you need to actually use it in the world, then you die while using it. Now, there's nothing wrong in figuring out the value of a policy by using it in the world. But to the extent you have a model of the world, you should be able to figure out how good the policy, how good a particular policy is, or how good a plan is, without actually doing it in the world. How would you do it here? If you were to write a little program for this, how would you have done this? What you would have done is, remember, A2, let's say, said, if you do A2 in S2, with probability 0.7, you go into S3, probability 0.1, you go into S1, and probability 0.2, you stay in S2. Suppose this, you know. Remember, this is what knowing the model is all about. If you know this, doing the action is not necessary. Get yourself a nice three-sided coin, which comes, side 1 with 0.7 probability, side 2 with 0.1 probability, side 3 with 0.2 probability. Toss it. And say that's what happened in the real world. That's the point of having a model. When somebody says, I don't have the model of the world, they don't have these numbers. When the kid has to figure out, okay, so I have this idea that I'll put my hand on the stuff and let me see whether or not it's a good policy. They can't think because they don't yet know what happens when you put your hands on stuff. So they'll actually go ahead and do it. But as you grow older, you have a model. And so you can actually evaluate the policy without having to do it. By the time you come to MDP, you have the model. So even though I said this as if you're doing it in the world, you don't have to do it in the world. You sample the world. Okay?
Are you saying like running in a simulator?
Yes.
Times?
Yeah. Exactly.
And how many times do you need to run?
How do you get averages? Essentially, you have to do it infinite number of times and sum divided by infinity. That is the expected value. Okay. But if you're doing it empirically, you just do n number of times, n being a reasonably large number. I'm just giving you. So what we are really computing is the expectation. Expectation is limit n tends to infinity. Okay, the sum of all them divided by n. That's what the expectation is. Okay? Yes?
So essentially you're taking all the possible values that you could get based off of whatever action you're doing and weighting them based off of the probabilities that you have?
That's essentially, when you said that, keep that thought to yourself. In essence, the way you are evaluating the policy here is computationally highly inefficient. You are acting as if the value of this state is completely independent of the value of this state, completely independent of the value of this state. But that's not true. Value of neighboring states are correlated. Now, what do I mean by neighboring? Neighbors are those that you can reach by actions. It's not physical or spatial neighborhood. I would say S15 is a neighbor of S1. If there is some action that I can take in S1, and once in a while that action will get me to S15. That's why S15 is a neighbor of S1. You see what I'm saying? And we think Pittsburgh is a neighbor because we can take a flight there. Okay? So now, because of the neighborhood, this sort of evaluation, if you did for S2 and then you also did for S3, the numbers are going to be highly connected. And it is that structure that you will utilize in computing this value function much faster in the next slide. But you need to first understand what valuation is and then go to the next level. Okay? Okay. Okay, so now for finite horizon values is what we're going to look at. In fact, it turns out that the same idea of value of a policy is done for finite horizon, infinite horizon, indefinite horizon, everything. But we will first start with the finite horizon one. Okay, so and we are trying to get a policy that maximizes the total reward over a finite horizon. Okay, and then basically that means find me a policy that will give rise to a value vector that is better than or equal to any other value vector corresponding to any other policy. It's a pretty tall order, right? Because I'm basically now going to look, in essence, at a power s times t policies to come up with the optimal policy. So when we finally figure out that there is a way of actually computing the optimal policy in time that's only polynomial in the number of states, you feel, wow, that's great. Because instead of being exponential, it is suddenly only polynomial. Okay. And the way you would do that essentially is to realize that the connection between the neighbors that we've seen in there. Okay. So anyway, this one is saying whatever I wrote here, that a value of a state now depends on the number of stages left to go. Remember, in the finite horizon value function, one thing that I actually did not say here, I mean, I should have mentioned it clearly, is that if in fact I am really looking for k horizon MDP, then V1 really is not a single vector of size S. It's k vectors of size S. The first vector says if you have k steps to live, what's the optimal thing to do in each of the states? Then that's what you will look into to figure out what action to do in the current state. Having done that, now you only have k minus 1 steps to live. So you then go to the k minus 1th vector. And then that too tells you what you're supposed to do in each of the states. So if you actually, in this particular case, after having done A2 in S2, you found yourself in S3. Now for S3, you don't look in the same vector. You look at, basically the pi now would be k vectors. So you look at the vector corresponding to the number of steps left. Right? In finite horizon, the policy itself, in a finite horizon, the policy itself is of size S times t, where t is the horizon. And so is the value vector, it turns out. In fact, the nice discussion we had here made it sound as if each state only has a single value. That's a single value if you only have k steps to go. And if you have k minus 1 steps to go, then the state has a different value. If you have k minus 2 steps to go, it has a different value. Now, to cut this whole thing, let me say the following thing. I want to find out the value of a state when I have 0 steps to go. What is it? You see that? If any of you didn't see it, you're in big trouble. Okay, that's our starting point. Okay, so V0. So I will write basically this as my notation, right? So it's value function with respect to policy pi with k stages left to go. Okay, k stages to go. And that is defined basically as the expectation over this particular cumulative reward you get. Okay, while you are doing actions with respect to the policy pi. And the policy pi, remember, has to tell you what action to do in a state given you have k steps left for all possible values of k up to the horizon. Okay, and the nice thing is, so this is basically what I just wrote here for the k step. Okay, this is the notation in terms of expectation notation. Okay, and so that's basically, this one is being then expanded here, where AT, the action you do is essentially in terms of, at action you do in state S that you reached with only t more steps to go, would then be picked up from the policy pi, with t steps that you completed. Okay, this is the number of steps completed. Okay, so that means the number of steps left over is k minus t. So if you find yourself after doing t actions in this state, and you need to figure out what action to do, then you ask your policy, what action am I supposed to do when I have only k minus t left? And then tell you an action, and that's the action I do. You get this? Okay? So the funny thing is, finite horizon MDPs are more meaner looking because the value function and the policy function are of the size of S times t, a huge number of numbers floating above. but they are much easier to compute. Okay, infinite horizon value functions will not be inner looping because the infinite horizon policy and value has to be horizon independent. Because if you completed 15 steps, how many more steps do you have left to go? Still infinite. So it cannot be horizon dependent. So for the infinite horizon value and policy function will be only of the size of state space S. So they look easier, but their properties are more subtle, because in fact even to show that such a value function exists is harder. Whereas here you can already see, for example, that V0, so you know, for example, that V0 pi S is always equal to R of S. That's your starting point. If I know this, then it turns out I can then, from this I can compute V1 pi S. And if I know V1 pi S, I can compute V2 pi S. And if I know V2 pi S like that, I can other way compute Vk pi S. And what I'm doing is dynamic programming. That's what we're doing. Okay? That's what. So you start by realizing that V0 pi S for any pi that you're trying to evaluate. Right now, remember, you're only evaluating the policy. Okay? So the idea in looking at this particular slide is you're evaluating the policy, and if you are given like 3 policies, then you will evaluate each of them, and then you'll get the value vectors for them and see which is the best. Okay, but actually we'll wind up doing better than that in just a second. Okay, so here V0 pi S is RFS. Okay, and Vk pi S is R of S plus, of course, so if you start from here and then you want to do, let's say, V1 pi S, what would you have done? That's the picture here. Suppose you happen to know the value for, if you had done V0 and then you know the value at V0, that is 0 steps to go for these 2 states. Okay, then I'm trying to compute the value of this state. Now this state, according to my policy, tells me what action I'm supposed to do in this state. Each state comes with an action that I'm supposed to do. And that action gets me to this state with 0.7 and this state with 0.3. And having gotten to this state, I get to live for k minus 1 steps. And here also I get to live for k minus 1 steps. That means the expected value I can get from here is is V k minus 1 pi S, which we have already computed. So now we can compute the Vk of S. So for each stage, you will compute the value for all the states, for that number of stages left to go, starting from 0. Once I got the 0th level, then I get the first level, then I get the second level, and so on, all the way up to k levels. Then I have computed the valuation of this policy. Okay? And this is where, in essence, I'm no longer playing this game of tossing coins, because I needed expected value. Okay, and actually I know that when I do this particular action, that this particular pi, so now let's go through this again slowly. So I have k stages. I'm trying to figure out k stage left to go valuation for state S. That would depend on the reward of S plus the expected value you get from each of the states you get into, having done the action that pi is asking you to do in S. Right? So this is why there is a summation here, and so this one is telling you that pi sk is telling me which action to do in S with only k steps to go. I do that action in S, I'll get into a state S dash with some probability t of that. This is basically the probability of going from S to S dash if I were to do the action pi of sk. So in this particular case, if I did this action, good. In this particular case, if I do this action, I got with 0.7 probability, I get into this state. Now, if I get into this state, then I will get V pi k minus 1 of this state as the expected value from then on for the next k minus 1 steps. So, I multiply this probability times Vk minus 1 pi of S dash. And I'm summing over all the S dashes I can get into given the action this particular policy is asking me to do. That's what is the expected value. So in doing this, you essentially got rid of actually doing empirical simulation. This is the obvious thing. I mean, you could have come here and some of you most probably would have understood it right away, but it's nice to understand these two because, by the way, it turns out that after this particular topic, we will get into reinforcement learning, where we will be acting like the kids who don't know what their actions do. And the only way they can figure out what their actions do is by doing them in the world. And by doing them in the world, they'll figure out these, they will approximate this model of the action. Reinforcement learning is learning these numbers. Okay? In doing so, it needs to actually execute it. By the way, for reinforcement learning to work, for kids to actually grow up, what must the worlds have as their property? Guaranteed to, for kids who come into the world, let's say, without any model and they have to still grow up and take classes, what must be the property of the world? What? No. What? No.
Like asking
What? What did you say?
Dynamic.
No. I'm really worried about being a kid that any of you guys might have. You're making the world dynamic. One guy makes it, I don't know, really worried about it.
What is benign word?
Benign. Benign is not a word that I've used till now. So you need to define what benign is.
So much deterministic.
What?
Stochastic.
Why is deterministic stochastic?
Reward. It should have some reward attached to it.
No.
Come
on, guys.
That's it.
I got it. Stand up. Stand up. Okay, clap for this guy. His kids will live. None of your kids will. Okay? Because, by the way, deterministic doesn't mean good world. You will deterministically die when you do this action. That's not good. Dynamic is certainly not good. So this guy will essentially put trucks in his living room so that the kid will learn how to live. Right? Ergodicity. The same ergodicity which made us do replanning and live is required for reinforcement learning to actually work. And is our world really ergodic? No. But is it completely non-ergodic? I mean, there's like a large numbers of states, percentage of states cannot reach one from other. That's not true either. Well, if it is true, we won't be here because our ancestors would have died long back and we won't be here. Okay, so when you go to the reinforcement learning, you will care about evaluating the policies this way. As dumb as it looks, this is the only way people who don't know the model will evaluate the policies. And by doing so, learn the model. In fact, since I cannot stop myself, I'll say the following thing. If I'm anyway doing this, one of the interesting things that we'll see when we get to the reinforcement learning is, should I even bother learning the model? Should I even bother learning the model of the action? Or should I just know what to do at each state? That's a subtle difference. All you really need to know to live well is to do the right thing in each state that you get. You don't need to know the model of the actions. And it turns out that there are two different kinds of reinforcement learning, which we'll talk about again when we get it. Okay? Model-based and model-free reinforcement learning. Any of you heard of Q learning in the class? I know some people are from robotics. Q learning is essentially a model-free reinforcement learning. It just says, I don't care about this intermediate thing, I just learned what's the right thing to do in each state. Okay? In fact, one can argue one can argue that we don't quite have good models, at least models that we can explain to our friends, for most of the activities we do, such as walking without falling down, such as bicycling, such as swimming. You just know what's the right thing to do. When I put you on the bicycle, if you have learned bicycling, you have figured out what's the right thing to do, which way to bend so that the bike remains stable. If I ask you, when you did this, what are the exact probabilities that you would have gotten into these different states? Say, I don't know. That means you don't know the model. You directly went model free. Okay, so when we get to reinforcement learning, we'll actually differentiate between model-based versus model-free learning. But anyway, so coming back to here, basically I just told you how to evaluate a finite horizon policy. So now to compute the optimal policy, one idea is loop for policy pi in a power s number of policies. For each of them, compute the value function and then pick the best using your maximization, maximum finding algorithms. Okay, that's already way better than this, because in evaluating the policy, you are essentially doing the dynamic programming, and then essentially you're just getting the valuation based value at k stages to go based directly on value at k minus 1 stages. But this loop will still be going a power s times t actually. A power s times t times. Now by could be the right idea, it's just that can we do it better? Okay, so that's what we'll look at in the next slide. The next slide, what we are trying to do is here, notice here in this particular slide, we essentially pick the action. We pick the action that the policy pi told us to pick. But if we are trying to figure out what the optimal policy is, then you need to try out each of the actions that each of the different policies could have told us, and see which one would have backed up the best value. Do you understand what I'm saying? Now here is an interesting thing. I already said this actually, for every pi, V0 pi s is always R of s. That means you have 0 steps to go. It doesn't matter what the heck your plan is. You'll get the immediate reward and you're done. Right? Okay, so now I will actually differentiate between Vk pi and just Vk. When I say Vk without a policy subscript, that means it's the best value over all the policies. Sometimes you'll also put star instead of pi. That's the best value. And you notice that this is already V0s. Right? Because V0 we know already, irrespective of what the policy pi is, this is the V0. Now I want to compute V1 in terms of V0. Just as we computed V0 pi in terms of, V1 pi in terms of V0 pi, I want to go directly from from V0 to V1 without caring about the policies. This is where it helps to realize that while policies are huge numbers, each policy at a given state can only differ in terms of which action it asks you to do. Suppose you only have 4 actions, that's what we had in our little thing. You only have 4 actions. So the policies can be different in different places. In this particular state, all the differences boil down to which of these 4 actions each of these policies are doing. So I'll consider all the policies. I'll do A1, compute for A1 this backed up value. And then for A2, backed up value. A3, backed up value. A4, backed up value. Take the maximum. That would be the best you can do. Do you see what I'm saying? That is basically the Bellman backup. And if this guy, by the time you're done with all the MDPs and non-MDPs, you'll get sick and tired of Bellman because he's the man. he came up with his backup function, and so you have to say Bellman everything. Bellman value, Bellman backup, Bellman value function, Bellman residual, Bellman this, Bellman that. So this is the map. Okay. So what's the Bellman backup in this particular case? It turns out that I'm trying to compute Vt plus 1. I don't know why I cannot say it. So Vt plus 1 in terms of Vt. Notice there's no pi. I'm just directly going in terms of optimal policies. Okay? So what I'm trying to do is, for every pi, there is a V pi. For a pi star, there would just be a V. And you can also call it V star, but you have basically the value function. If I compute this directly, then I can recover pi star. And in fact, most of the normal methods for MDPs do this notion of value iteration and value change. Okay, in this case, it's not different. So basically, you have V0 always, and because of V0, you can get V1. Because of V1, you can get V2, etc. The only difference is now, suppose in this world there are only two actions, A1 and A2, that could be done. There are only two actions, A1 and A2, that could be done from state S. I'm going to compute, given that I've already computed T stage to go value function for all the states. I'm ready to compute T plus 1 stage to go value function for each of the states. And I'm now looking at S. And S can do either A1 or A2. If it does A1 with 0.7, it goes to S1, 0.3, it goes to S4. If it does A2 with 0.4, it goes to S2, 0.6, it goes to S3. So I can compute essentially, okay, let me just remove this stuff so that I can compute essentially that the red part is basically would get this expected value. If you were to do, that shows red by the way. I'm not colorblind, but this shows brown here. So this A1 part corresponds to this. This is the expected value, 0.7 times Vt of S1 plus 0.3 times Vt of S4. That's what you get if you do A1. If you do A2, which is the other possibility, then you will get 0.4 times Vt S2 plus 0.6 times Vt S3. Because A2 is going to S2 and S3. And with these probabilities. Notice these numbers were known because you knew the model. It's been given to you. In reinforcement learning, you won't. So you need to figure this out by doing it in the board. Okay, so you got these things. So if you go this way, you get this much. If you go this way, you get this much in this stage. What are you trying to do? Increase your value for the state. So what would you do? You would take the max of these two. Max of these two. To that you add the immediate reward of S. That would be Vt plus 1S. Done. I just explained to you finite horizon Markov relation processes, how to compute the optimal value function. Once you compute the optimal value function, you're done. What is the policy, by the way? You just remember which action you picked everywhere. That's the action to pick. Do you see what I'm saying? So in this particular case, you got the maximum through which, by the way? Well, I guess depends. I didn't tell you Vt of S1 and Vt of S4. If I add the real numbers for those two, then one of these numbers has to be bigger than the other, or both are equal. If they both are equal, then each action is equal. You could have picked either of them. If one of them is better, then that is the action that you are picking. That's how you are computing the policy along with the value. Yes?
So in here we only have two policies, yes?
What?
In this case, we only have two.
No. I don't know. I mean, first of all, I didn't tell you how many states there are. I certainly didn't tell you how many total number of actions there are. You could not. Suppose it turns out there are only 4 states. only 4 states, and suppose it also turns out that the maximum number of actions in any place is 2, right? Then it is 2 power 4 times the number of time steps in the horizon. Did you get that? Okay. In the most, this picture doesn't tell you the entire MDP. It's just telling you one particular background. The most benign interpretation of this picture is that there are at least 4 states, because there are 4 states here, right? And then the maximum actions maybe are 2. You know, that's the most benign thing. That's the most benign thing. Maybe it's 2 or less, let's say. So imagine it's 2. Okay. Then essentially for each state, you're trying to take one of 2 actions. So 2 power 4. And you need to do this for each one of the time steps. So 2 power 4k, where k is the horizon. That's what this picture is showing. Okay? Yes?
And to calculate VTS1 and VTS4, do you also do the equation again? Like
Yeah, remember we always go this way. I'm showing you in a minute. I'll show you the full, end-to-end thing. But notice that by the time you ask yourself what is VT plus 1, you already computed VT. Because you start always with V0, which is 0 steps to 4. That's the reward. Once you get V0, you get V1. Once you get V1, you get V2. Once you get V2, you get V3 and so on. For finite horizon, there's a nice flow. One of the nice things is the moment we get into infinite horizon, you would like to see this kind of a flow. So the original algorithms we will come up with would be what I call synchronous value iteration algorithms that sort of tend to update all the states to one state, then re-update all the states to the next state and so on. And then people basically figured out that given that it's infinite horizon, it doesn't really matter whether the updates are done synchronously or not. As long as every state is updated infinitely often, it doesn't matter. Again, many of these things, when you get that, my hope is that some of these digressions I'm making, when I get there, you have heard it the second time. So at least you would look, as new. Okay, so go back to this example. So the value iteration finite horizon case, that is your actual specification, right? So you start with V0, right? And you start with V0, and you then basically do this Vk in terms of Vk minus 1. Okay. And then having computed this, you need to compute pi star. Actually, this particular slide, the notation would have been much better if you think in terms of V star k. Okay. Because star somehow is the best value function. Okay. And from V star, you get pi star. Of course, you could have, because V already has superscript, the number of time steps to go, it was hard to put a star there, so they just went with just V. But think in terms of, this is the distinguished optimal value function, which then is directly connected to the distinguished optimal policy. And how do you compute the optimal policy? If I actually gave you, so one way of computing the value function, policy, the policy is as you are making these decisions, you remember which was the best action you picked here. However, suppose I just basically went through my computations very fast and did not remember which actions I picked. I'll come and give you the optimal value function. Can you recover the optimal policy from it? This is a very important question because you wind up doing this all the time. This is also like the most basic thing you do in reinforcement learning. Okay, so this is basically what I'm saying here. So if I were to tell you, let me write this here because again, so suppose I was to tell you, I already computed a value function V star. Okay, now I'm trying to find out for Vs with k steps to go. So for S state S with k steps to go, what is the action that I'm supposed to pick? Right? Again, you know what actions could be done. Suppose A1 can be done, suppose A2 can be done, suppose A3 can be done. Now, I know A1 can get with 0.7 to S1, 0.3 to S2, A2 can get 0.5 to S4, 0.5 to S5, A3 will just with 1.0 probability go to S5. That's my model. So which is the best action to pick? Well, I know Vk minus 1 of these guys. So then I can compute the expected valuation for each of them. So basically, I will redo this step as needed, just to remember what action I forgot to remember. Right? It's better to actually remember on the way, but it's nice to know how to convert a policy and a value into a policy. Now, if you do this, and if your value function is the optimal value function, you get optimal policy. If you do this, and if your value function is not optimal value function, basically all you are doing is you are getting what's called a greedy policy. So you have some approximate idea about what is the long-term value of each of these states. And using that, you're trying to figure out which action I would do. I'll pick that action that is expected to take me to states that have higher long-term value. Now, since I talked so much about reinforcement learning, remember that in reinforcement learning, you will never know the optimal value function because you don't know the full model of the world. You know some of the value function, some approximation of the value function. So an agent can do greedy policy. With respect to its current value, it can pick the action that maximizes the value. But its understanding of value is flawed because it did not compute the optimal value function yet. So the only way it can hopefully, even if in fact the world is ergodic, the only way a reinforcement learning agent will reach, is guaranteed to asymptotically reach an optimal value function is if it goes off greedy once in a while. It has to stop being greedy. Okay, so for example, you took elementary school, high school, you figured out how the world works. The temptation is extremely high that you should start exploiting the knowledge you got. Take a job. Now, whatever best job that's available. So you would basically look at, Burger King and McDonald's and Jack in the Box, and from Jack in the Box is paying higher salary per hour. So you make the optimal choice based on your current knowledge of how the world works. Right? That's greedy action. It's way far from the optimal action. And you don't know what you're missing, because you don't even know what other states are available and what actions can get you to what states. In reinforcement learning, that's your predicament. So what do? You have to explore, in addition to exploit the current value function. If the value function that you currently have is already optimal, why bother exploring? Then nothing that's going to change. If your value function is not optimal, then you have to explore. Otherwise, the policy you are following will not be, you will never get to the optimal policy. Okay. Again, in this case, since we already computed the value function, in this case, since I've already computed the value function, okay, the optimal value function, so I can pick the best action, and that the greedy policy also turns out to be optimal policy. So what is defined for any value function is, given a value function v, there is a pi that is greedy policy. It so happens that if v is optimal, then the greedy policy with respect to v is also optimal. Okay? And and if you look ahead for the reinforcement learning, this is where essentially the exploration versus exploitation trade-off comes in. The only way you can figure out better value function is to, with high probability, do what your current, remember what's the thing? Once in a while, stop and smell the roses. Okay, all these things essentially are saying, once in a while, do the thing that's not the optimal policy that you have carefully constructed. It would be a very namby-pamby thing to say to somebody who knows how the universe works and have constructed the optimal policy. Why should they stop and do something that is not according to their optimal policy? It's the right thing to say to us because none of us have the full state space or the full model. So whatever policy we got is the greedy policy. A greedy policy exploits your current value function. To get from there to the real value function, you need to throw in actions that you never did before. That's the exploration. When you're doing exploration, you take a hit. Unless you guys are getting really good teaching assistant salaries or whatever, when you go to school, you take a hit in terms of salaries, right? But essentially, you are doing that because you can then go to a much better policy. Because then you'll know more about the world. And that all can be understood formally in the MDP model. These are analogies, but there's formal connection here. Okay, so that's value validation. And here's an example. We'll just go through. So there are 4 actions. You should do an example yourself. Homework requires you to do some examples. So you should do one of them yourself if you want to make sure that you understood it. So you have S1, S2, S3, S4 here. So for V0, I already know what the value function is, right? Because that'll just be R of S1, R of S2, etc., R of S4. Right? Now, when I'm computing V1, essentially, let's say I'm looking at, for V1, I need to compute the values for each of the states again. So now I'm focusing on, let's say, this state. If I'm focusing on this state, suppose there is one red action that I can do, one brown action for you that you can do. Believe me, this is red here. That's 0.7, 0.3 to S1 and S4. And then you can also do this, what is really brown for me, for you, yellow action. That's 0.4, 0.6. Okay? And then you compute the expected value for each of those actions, take the max of that, and take R of S4, add it to that. That would be V1 of S4. That's all. And you do this for all the states, then you got V1, then you can compute V2, then you compute V3, etc. So I'll just go a couple more things. So then for the rest of the guys, I'll compute the best action, then I'll compute V2, then I'll compute V3. And if I'm only doing a 3-horizon MDP, then I got the full value function now. And from that, I also got the optimal policy. That's finite-horizon Markov process. Okay? Right? And what we did just now is basically the maximization step is the Bellman back. You consider from your state all the possible actions you can do. Pick the action that will get you the maximal backed up reward. Now that estimate is just as good as your estimate of how good these states are if you have k-1 steps to go. In the finite horizon case. If you're in the tth step, then this is t-1 steps to go, right? Now, think again ahead and think of infinite horizon Markov processes. You can play this game for the infinite horizon Markov process. In fact, that's what you do, almost with a minor change, which we'll discuss in a minute. Infinite horizon Markov process just work like this. Okay, obviously you're not going to draw this infinitely long. Okay, what happens essentially is what happens essentially is that you always have the current approximation to the value function. So here the value functions have semantics. V0 means it's the optimal value function and you have exactly 0 steps to go. V1 means it's the optimal value function and you have exactly 1 step to go. For an infinite horizon, it doesn't make sense to talk like that because that would mean as if there are infinite number of value functions. What you really have is approximation to the single V star value function that will always ask you to do the same action for the given state. But you're trying to approximate that value function. Current V0 is your 0th order approximation. V1 is the first iteration. V2 is the second iteration. V3 is the third iteration. The iterations in the infinite horizon Markov processes look just like, stages to go here. Except, basically, they're just iterations. They don't have any semantics. And you will stop iterating when the value function from one stage to another stage doesn't change. Right? If this value function and this value function are the same, that means this vector and this vector are the same, why back up anymore? And since we are talking about real numbers, they may never become exactly equal. So, you would say, well, I would not look for exact equality. I will say, when V2 is only epsilon away from V3, where epsilon basically is in terms of the maximum. So you have V1, V2 and V3 are both, Vi and Vi plus 1 are both a S-sized vectors. S is the size of number of states, S-sized vectors. Distance between these two is, you can define in terms of maximum, which is basically take the differences, absolute value of the differences between each of the dimensions. For S1, what is this guy saying, what is this guy saying? Take the difference, take the absolute value. For S2, for S3, etc. And take the max of all these differences. That is the maximum. One vector is different from the other vector, any need place. If that is less than epsilon, I stop. I would stop going forward. That is basically what infinite horizon Markov processes do. Okay? Now the only question is, let me go there. Okay. The only question is, what makes me think that as I add up the cumulative reward I am getting, as the number of iterations go higher and higher, what makes me sure that everybody won't wind up becoming equal to infinity? The value function for every state will become infinite. If all the states have infinite values, then there is nothing you can do. Basically, it's like a degenerate problem where you have no idea what action. Did you guys get this? In finite horizon, this is not a problem because you're only doing finite number of iterations. In infinite horizon, we are saying there are infinite number of, there could be indefinite number of iterations, and we are hoping that at some point of time, the value function will converge. If it's becoming infinite, it's not going to converge. What makes you think it won't become infinite? What makes you think that if you were to live infinitely long and you add up the sum of the rewards, it won't be an infinitely large number? Nothing can make you think that. Okay? So the only possible way is to remember what did we do to make infinite sequences, infinite series sum to finite numbers. We have seen power series. Okay? A power geometric series will always sum to a finite number if the common ratio is strictly less than 1. If you don't know what I'm talking about, quickly go back and remember what geometric series is. So A plus AR squared plus AR cubed, where R is the common ratio. Okay, if R is less than 1, strictly less than 1, if the magnitude of R is strictly less than 1, you know that the sequence will actually converge, and will converge to A times 1 by 1 minus R sum. Okay, that's the calculus you learn, right? And that's what we'll wind up using. Now, how do I do this? I somehow have to throw this R square, R cube, etc. Okay, now that basically is where we essentially do this trick. And we say, that if I am on state S, I get my reward R of S. I'll get it directly. The next state will give me R of S1, but since I'm sitting here, the reward I get there from here doesn't look equal to R of S1. It will look equal to beta times R of S1, where beta is a discount factor. So I discount future with respect to where I am. So if you're going to give me $1 right now, I'm very happy. If you're going to give me $1 one step from now, I'm only beta times 1 happy. If you're going to give me $1 two steps from now, I'm only beta squared times 1 happy. And if you're going to give me $1 infinite steps from now, I'll be beta power infinite times 1 happy, which is 0. Because any number, which would be 0, as long as beta is less than 1. Right? I mean, woe be unto you if you pick beta to be 2. And you're dead. And you got to be a bigger problem. I mean, you really like future. You don't care what's going on with your life. You only like future. I mean, the interesting thing here is even those people who seem to look as if they understand the value of future and actually trudge all the way to graduate school have beta less than 1. Otherwise, for them, every action looks equally good. You understand what I'm saying? The only difference between the grad school people and the undergraduates are the MS students and the PhD students is their beta value. Right? I mean, in this view. So who has bigger beta? In this analogy. PhD students have bigger beta. Because $1 2 days from now for them is 0.999 square times $1. For the MS students, maybe it's 0.7 square times $1. For undergrads, it may be 0.5 square times $1. For the high school dropout, it may be 0.1 square times $1. This is what I'm saying. So again, connect, if you change the beta, then it tells you how severely are you discounting future with respect to current time. Discount you must if you want to live infinitely long. Because if you want to live infinitely long and you don't discount future, then everything looks equally good for you. Once you do that, essentially, and I'll show this slide and then we'll come back next class. Once you do that, this is the only update that you will be doing. This is the celebrated Bellman update for Finite-Horizon Value processes. Okay, so V star S, essentially the optimal value function V star S is related to the optimal value function of the neighbors V star S dash in terms of the Bellman equation. Okay, now where is the discount factor coming? This is where it's coming. Because with respect to this guy, because it's in S, you'll get R of S, which is the reward, plus this is the expected reward he or she would get for each of these actions A. You take the max, that's the best action you can do. But then you don't directly add it, you have to multiply it by beta and add. The moment you multiply it by beta, then this essentially is going to be a convergent. This sets up a V star, so you can compute. This is a bunch of equations. It's a bunch of equations on S variables. S is the number of states. Why can't we just solve this set of equations? We have MATLAB. The problem is the equations are nonlinear. There is a max term in it. So you cannot solve them that easily in MATLAB. In fact, one other thing that you can think of is instead of V star S, we're thinking in terms of V pi S. That is, given a policy pi, what is its valuation? The same exact equation holds, except instead of max, you will just, instead of doing action A, you do pi of AS. Whatever the policy says, you do that action. That way you will get the policy's value. There you could be a sequence of linear equations, you can solve them to get the S value, the values for the states. Here you essentially have a max going on, so it's not a sequence of linear equations. This is a series of nonlinear equations. And the way you will actually compute V star is by value iteration, wherein you pick some value, current values, some approximation to that value function. Initialize the value function to, the V0 iteration, you can initialize the value function to any value you want. Something you can do is just initialize to R of S, but that's not required. And V1 of S in terms of V0 of S by using this equation. Instead of thinking of this as an equation, think of it as an update function. And keep updating. V0, from V0 you go to V1, from V1 you go to V2, from V2 you go to V3. And when Vi to Vi plus 1, the value function hasn't changed too much between two iterations, you stop. That's infinite horizon operation. And those of you who see that something like this has been done in stuff like PageRank, for example, you are not dreaming. Basically, that's also a fixed point computation. And you essentially computed the fixed point iterator. We'll stop here.